Hey, physics students and all those who love physics. Here's a video on force on a current carrying conductor placed in a magnetic field. This is a very important concept, and the force is given by I L cross B, where I is the current in amperes, L is the length of the conductor, and B is the strength of the magnetic field. The strength of the magnetic field is measured in Tesla. The length of the conductor is in meters. And of course, I is in amperes. And that's when you get the force in newtons. It is important to know this concept because it is the fundamental principle of operation of current or voltage measuring instruments. And that's why I'm going to give you an example of a problem and how to work it out so that you have a better understanding. So this question talks about a 2-meter long wire carrying a current of 8.2 ampere, which is immersed within a uniform magnetic field B, which means it's kept in that magnetic field. When this wire lies along the positive x-axis, a magnetic force given by negative 2.5 J Newton acts on the wire, and when it lies on the positive y-axis, the force is 2.5 I minus 5.0 K newtons. You got to find the strength of the magnetic field. Alright, so the strength of the magnetic field B is equal to Bxi plus Byj plus Bzk. So we are assuming that the magnetic field has all three components. I, J, K are the unit vectors along the x, y, and z axis. And in the first case, the conductor lies along the plus axis. And that is why we have L is equal to Li. Now the force is given by I, L cross B, which is equal to, the current is 8.2 amperes, so it's 8.2, and then you set it up in the form of matrices, where you have I, J, K, and carefully put the coefficients of the length first. The length only has a coefficient for I, which is 2 meter, so 2, 0, 0, because it lies along the x-axis. It has no components along the y and z. And that is for the magnetic field, and Bx, By, Bz. And then take the product, and hopefully you know how to take the product. When you do the I, it's going to be 0 times Bc minus 0 times By, both zeros. When you do the J, you got minus J 2 times Bc minus 0, but there is an 8.2 outside, so 2 times 8.2 gives you negative 16.4 Bcj. When you do the K, likewise, you're going to get 2 times By, which is again 16.4 Byk. Everything else is 0, and that should be equal to negative 2.5 J given. And so now you take the coefficients of each one and put them equal. You can see the coefficient of J on the right side is negative 2.5, and so negative 2.5, and on the left side is this whole thing, negative 16.4 Bc. All right, from that you can just find Bc. You get it as 0.152 Tesla. And By is 0 because on the right side there is no coefficient for K. On the left side you do have this coefficient, so that's why By is 0. Now in the second case, you do it similarly. This time, the conductor lies along the positive y-axis, and so it should be Lj, because j is the unit vector along the y-axis. And just like before, Fb is I, L cross B. The current is again the same, so set it up as 8.2. Use matrices IJK. This time it's going to be 0, 2, 0. So that's the IJK coming up. Why is it 0, 2, 0? Because it's lying along the y-axis. And then Bx, which we did not know, By is 0, determined from the previous case, and Bz is also been found out. So again, do the same thing as before. You say for I, you go 2 times 0.152 minus 0. So you have this 8.2 out. So that's where you're going to get 2.5i when you multiply 8.2 with 2 and then with this. So do the same for negative j, you get 0 for both. For k, you're going to get 0 times this minus 2 times bx. So that's why you have that negative 16.4 because of the 8.2. Now put the coefficients equal to each other. Negative 16.4 bx is the coefficient of k on the left side, and on the right side it's negative 5. So that's why I've put them equal to each other. Right? Negative 16.4 bx is equal to negative 5. And therefore bx should be equal to simply 5 divided by 16.4, which comes out to be 0.305 Tesla. So now we have the x, the y, and the z component of the magnetic field. And therefore the magnetic field is B is equal to 0.3I from here plus 0j, which we're not writing, plus 0.152k. So that is how this problem is done. I know I went through this a little bit faster, but I hope you understood. Thank you.